So now what we're going to do now is shift gears a little bit and introduce Dr. Zining Wu. He's the co-founder and CEO of InnoGrit Corporation, which is a semiconductor startup focusing on data storage, management, and processing. Before founding InnoGrit in October 2016, Dr. Zining Wu worked at Marvell for 17 years, where he last served as the CTO of Marvell Technology Group. In this role, he was responsible for overseeing all the technical aspects of the company, including establishing the company's technical vision, directing strategic initiatives, and managing central engineering. Prior to his CTO role, Dr. Wu was the Vice President of Data Storage Technologies at Marvell, where he was responsible for innovative storage technologies for hard disk drives and SSD controllers. And on a personal note, he also is a Stanford graduate. So help me in welcoming Dr. Wu, please.
Well, thank you, Jim, for the introduction. Hello, everyone. Welcome to the last keynote before the panel discussion. Before we start our presentation, let me ask all of you a question. How many of you are on 4G LTE network for your cell phone? So almost everyone, right, as expected. It's great. So we know that when we got 3G a couple years ago, our first reaction was it was so fast, so cool, right? But now, today, we have 4G, not to mention 5G coming. Would anyone want to go back to 3G? Of course not. It's too slow. Today, the same thing is happening in our world of storage. Today, I'm going to show you how InnoGrit will transform, will revolutionize storage industry, like from 3G to 4G network. You may wonder, who is this guy making such a bold statement? As you can see, my name is Zining Wu. I'm the CEO of InnoGrit. In the next 20 minutes or so, I'll show you how InnoGrit will speed up the storage technology, like the 3G to 4G transformation, and how we'll process data much smarter than before. So before we dive into technical details, let me give you a brief introduction to InnoGrit. InnoGrit was founded in year 2016, October 2016, by a group of industry veterans. Since then, we have been working on cutting-edge storage controllers, focusing on the highest performance and the lowest power. Our controllers cover every usage from BGA SSD all the way to data center applications. So we all know today we're undergoing a data explosion. No need to explain this chart because we all feel it every day. In 5 years, there will be 175 zettabytes of data in the world. So applications will access more and more data. But at the same time, data access needs to happen faster. Like what we talked about from 3G to 4G network transition, remember that once people get used to faster data access, they won't tolerate slower data access. So it is shown that a 0.5 second delay in page loading leads to 10% difference in sales. For a big online retailer like Nordstrom, that 10% translates to over $1 billion. Google also showed that a 0.4 second delay in search leads to 0.44% drop in search volume. Since Google generates more than $100 billion a year from search-related revenue, again, we are talking about hundreds of millions of dollars for just less than half-second delay. So it is very obvious that accelerating data access is good for return on investment. However, accelerating data access is not simple because today, even a single job like a search job, right? We think that's simple, that's straightforward. It involves many microservices. For example, getting the user history, fetching ads from ads inventory, and do a real-time auction. All this requires each microservice to fetch data from a large database and run processing to score them and render the final result to users. So to accelerate the data access, we need to make data fetching and processing and transfer all of them faster. Today, if we want to get some data from a remote server, it takes over 120 microseconds, with the SSD access time being the highest part, the largest delay here. But other parts, like networking delay and software delay, are also significant. However, in the last 2 years or so, people have developed NVMe over Fabric technologies that has been shown to reduce the network latency from 20 microseconds to less than 5 microseconds. And there are also new file systems, user-space file systems, that shorten the software delay from 10 to 20 microseconds to below 5 microseconds. So now the SSD delay, SSD latency is the dominating factor. The good news is, in the last couple of years, there have been new technologies for storage media, such as low latency NAND, MRAM, RRAM, phase change memory. We call them storage class memory. And their access time, or TR, are only several microseconds. Some of them are even lower than that. So at InnoGrit, we found a way to build low latency SSD based on those kind of storage class memories and reduce the SSD latency dramatically by almost a factor of 10. So with that, combined with advances in network and software, we can reduce the overall access time by 85%. To show how it works, let's take a look at today's system. The read latency today mostly come from flash TR, right? Flash read time. Right? So in the case we need to access 4 kilobytes of user data, the flash itself takes about 50 to 70 microseconds if we are using today's dominant TLC. Then on top of that, the controller adds about 15 to 20 microseconds. Then transferring to host takes another 1.2 microseconds if we implement a PCIe Gen3 by 4 interface. However, as we have heard from day one, right, from Toshiba's keynote, we know that their latest technology, XL Flash, can reduce the flash access time to 3 to 5 microseconds. We at InnoGrit developed new ECC architecture to reduce this controller delay to 5 microseconds. And then on top of that, we also implemented PCIe Gen4 interface to reduce the transfer time by half. So combining all of them together, we have an SSD system that can deliver the overall latency in just 10 microseconds. You may think I'm bluffing, so let's take a look at our latest result from our latest controller, Tacoma. This is the real silicon result. As it shows, combined with XL Flash, when the I/O depth is 1, we can achieve a 10 microsecond delay. That's almost 10 times better than the conventional TLC. And as a result of that very short latency, we dramatically increased IOPs, I/O per second, when the read depth is very low. Right? From read depth from 1 to 8, we increased IOPs by more than 3 times. So with a combination of SCM and a carefully designed controller, we can achieve a very fast storage. But as we know, SCM, capacity-wise, is really small. So it's like we build a fast and small race car. But as we showed in the first couple minutes, the data set is getting bigger and bigger these days. So what we need is not just a fast and small card, but what we need is a big and fast and big storage, like a bullet train. Right? So a natural way to build a big and fast storage is to combine the traditional TLC with the fast SCM. Right? Because we all know that SCM, even though it's fast, is expensive. So if we build a whole large system with SCM, the cost is too high. On the other side, TLC is cheaper, but much slower. If we combine a system with 80% of TLC and 20% of SCM, we expect to get a better system that means faster than the TLC itself and also less expensive than the SCM. So we try to get better of both worlds. However, if we are not careful, we may end up not with a fast and big storage, but rather a slow and big storage. So the key to make such a mixed system work is to put hot data in SCM, so we have fast access, and put cold data in TLC to reduce cost. But how do we know data is hot or cold? One way is to let user application tell us. If the application says, my data is hot, it will be placed into SCM. Otherwise, it will be put into TLC. Such hints from applications should be very accurate. However, it can have other problems. For example, if such a system is used in a multi-tenant environment, there may be multiple virtual machines running on one storage box. Then if every application says my data is hot data, there will be contention. And that defeats the purpose of separating the data into cold layer and hot layers. Also, hints from application may not have temporal informations. That means hot data in today's computation, today's access may not be hot tomorrow. If the application stop in between, it may not tell the storage system. And the storage system may still think the data is hot even after several days. So we need a way to tell hot data from cold data, to do the prediction reliably in a virtualized environment, and also to do it to consider temporal information so it's self-adaptive as time goes and when the usage scenario changes. Luckily, such technology is readily available today. In the last couple of years, neural networks have made great progress in doing very difficult classification problems, like speech recognition, image recognition, and so on. With neural networks, it can train itself using data and can do the prediction without human intervention. So in that way, since neural networks don't need hints from applications, it can predict data reliably in a virtualized environment to provide system-level fairness. And also, neural network will be self-adaptive, so it can take temporal information into consideration and also change itself when the use scenario changes. So at InnoGrit, we built just a system like that. So before we dive into the system itself, let me ask a quick question of you. How many of you know the basics of CNN networks? Okay, quite a few. Okay. Let me just give you a brief overview of how CNN or convolutional neural network can be used today to predict or to do image recognition. It involves several steps. First, the images go through convolution engines to extract its features. Then the features are sent into the pooling step to reduce the feature size. So at that point, only the most dominant features are considered. And then the most dominant features go through the pooling, goes through the fully connected network, and the output of fully connected network are scores. So in this example, the scores represent how likely this image is as a tree or a cat or a dog. And the highest score goes to the dog, so we can label this image as a dog. It turns out that the same techniques can be used to distinguish hot data from cold data. Think about it. Binary images are just like binary data. If we can build a predictor or classifier to tell the difference between a dog or cat, we can apply the same idea and analyze binary data to predict its hot data or cold data. So at InnoGrit, we did exactly that. We applied the principle of neural network, but we trained the model differently, of course. It's not for image recognition, but it's for data recognition. So we tried it first with some PC user data. We achieved 99.94% accuracy, very high accuracy. Then we applied the same approach, but trained a different model for enterprise data. This time, we used SPC Financial 1 dataset, and we achieved 94.72% accuracy. So with that kind of accuracy, we can build a hot data, cold data predictor into our controller. This predictor uses neural network techniques and uses hardware engines. The input of the predictor is data, right? User data. The output are hot data, cold data flags. And those data flags are used by the storage management block. The storage management block then places the hot data into the SCM and cold data into TLC flash. So at InnoGrit, we built exactly such architecture, and we call it Tacoma architecture. It uses embedded CPU and hardware neural network accelerators to do data prediction. So according to the prediction, it's hot data or cold data, the data will be placed intelligently into SCM or TLC. For hot data, it goes to SCM. And SCM, as we just showed a couple minutes ago, has a very short latency, 10 microseconds with XL flash. And if it's cold data, it goes through TLC. And since we implemented PCIe Gen4 interface, even the TLC phase, TLC path has very high bandwidth, over 7 gigabytes per second. So overall, Tacoma is a very high-performance controller for data storage. Its sequential read can achieve 7 gigabytes per second, and sequential write can achieve 6.1 gigabytes per second. And the random read can hit 1.5 million IOPs, with random write over 1 million IOPs. And as we just introduced, with low latency flash, like XL flash, it can achieve 10 microseconds delay. Of course, Tacoma has all other high-end features for data center and enterprise applications, like NVMe 1.4, multiple namespace support, end-to-end data protection, atomic write, SRIOV, hardware crypto engine, and of course, the neural network accelerator that we just talked about. So how does this Tacoma architecture, this Tacoma controller, help the end user? Well, we try to run some user-specific storage tasks on this controller and time it. So we try different systems. First, without any XL flash, that's just a traditional system. It takes 175 seconds to finish this user trace. This user trace involves a lot of data read and write and retrieval. So a lot of heavy data processing, data storage access. So it took about 175 seconds for the traditional system. If we add SL flash into the system, but now doing AI labeling to separate hot data and cold data, now to place it intelligently, we get some improvement, about 29%. That's shown in the middle bar. And if on top of that, with XL flash, and we use the AI labeling we just talked about, it further reduced process time by another 20%. So overall, we reduced the process time by almost half. That is, we increased the system throughput by a factor of 2. At this point, you may ask the question, how feasible is this system? How much data do you need to train the system, to train the model, to get such high accuracy? And what if the usage case change? It turns out that's not a problem. Because as we have shown here in this chart, this system is very self-adaptive. If we start from untrained data, it takes only about 250 batches of data to get to 85% of accuracy. And takes about 3,000 batches of data to get to 95% of accuracy. Remember, we have a PCIe Gen4 interface with a throughput over 7 gigabytes per second. So 3,000 of batches of data can be finished within 0.3 seconds. So our system is very adaptive, and it can accommodate different usage cases easily. So by now, I hope you all get the idea that we can build future system much faster by using storage class memory, SCM, and properly designed controller that offers ultra-short latency data paths. And we can also make the system much smarter by combining programmable CPU and a neural network hardware accelerator. We have shown by using the faster and smarter storage controller, we can increase the storage throughput by a factor of 2. I hope by now you are all interested in our faster and smarter small storage, and please come to visit us at booth 814 before we finish this afternoon. Thank you.